That's something I do. Okay, so we are going to talk briefly about alkyne reactions at the beginning of class today. Overall, my goal for class, can everybody hear me okay? I know that I'm kind of loud, but I know that there's also a lot of loud sounds outside. So we're gonna briefly talk about alkyne reactions. I do have a beautiful alkyne reaction table, just like I had for the alkene reactions, that I will be posting a answer key to after class. So you will have access to that if you want to check on that. After we do these slides, I am going to go over a synthesis problem as well that you can listen in on, or you can choose not to, just to give you guys a little bit more practice with a quote unquote synthetic mindset. And then we have worksheets and all of that fun stuff that you can work on. Okay, so overall, there are 4 things that you can do with an alkyne. And the really great thing about alkyne reactions is that there's a lot of repetition. All of the same reactions that we saw that we could perform with an alkene, we can also perform them with an alkyne. And this is great because you have to memorize half as many reactions as you would if there wasn't any sort of repetition. So the only difference is you cannot turn an alkene into a good nucleophile, but you can do that with an alkyne, but this is something that we've talked about with exam 2. We know that we can add some sort of a good base like a hydride reagent and deprotonate a terminal alkyne, and this will allow us to generate an organometallic. Other things that we can do with alkynes is we can reduce alkynes by adding hydrogens, halogenate alkynes by adding halogens, and hydrate alkynes by adding oxygens. Now, just to highlight the similarities and differences of alkene and alkyne reactions, we're going to go over one example where we look at hydration with hydroboration oxidation. So this is a reaction that we can do both with alkynes and alkenes. And we see that in both of these reactions, in the first step, we react with a boron containing electrophile. In that second step, we add oxidative conditions where we have our hydrogen peroxide and sodium hydride. We also see that when we look at the products, we're adding a hydrogen to the most substituted carbon and an oxygen to the least substituted carbon. So if we're adding a hydrogen to the most substituted and an oxygen to the least substituted, what type of addition is this? What is the regiospecificity? So it won't be Markovnikov, because Markovnikov wants us to add the hydrogen to the least substituted carbon. So in this case, it'll actually be anti-Markovnikov. So we see that both of these have the same regiospecificity. They're both anti-Markovnikov. This is great. This is another similarity. And the differences lie in the fact that we see that for our alkyne reactions, for an alkyne, we end up with a carbonyl, whereas for an alcohol, we end up with an alcohol. And this difference is actually explained by the difference in our boron-containing electrophiles. Now, it is a fairly common theme where our alkene reactions will add alcohols, whereas our alkyne reactions will add carbonyls. So if we look more into these boron-containing electrophiles, or I should say, does anybody have any questions first before we continue? Okay. So if we look more into these boron-containing electrophiles, we can see that it actually makes sense with why we form a carbonyl from alkyne conditions, whereas an alcohol from alkene conditions. And that's overall going to be due to the equivalence of hydrogens, or the number of hydrogens present bound to that boron. So with an alkyne, you can only reduce or you can only, that was a really squeaky noise. You can only reduce one pi bond because you only have one hydrogen. So since you're only using one hydrogen and reducing one pi bond, the other pi bond will be retained in that carbonyl. So that is kind of the explanation as to why. And having little explanations like that can be useful memory tools because it's always easier to remember a story than to remember an isolated fact. So there are definitely similarities, but there are also key differences. And it's important to recognize those differences. Those differences are valuable, but it's also good to create a network of the similarities while you're studying these reactions. So how do we feel about all of this? Good-ish, okay. The last thing that I want to know is just to trigger your memory if you have forgotten it, is this idea of tautomerization. So when we're talking about tautomerization, we're talking about the interconversion between two different tautomers. So tautomers are constitutional isomers. Who remembers what a constitutional isomer is? Yeah. So a constitutional isomer. These are isomers that are going to have the same molecular formula. Any isomer always has the same molecular formula, but they're going to differ in their connectivity. So the bonds are arranged in a different order. The atoms are attached in a different way. And we see that here. These are constitutional isomers because they're going to differ in the location of this hydrogen right here, as well as this pi bond. So you can convert between the enol form and the keto form of these tautomers. And just as a reminder, the keto form is going to be almost always the more stable form. The only time that the keto form will not be more stable is if the enol form is part of an aromatic ring. So how do we feel about this? So in the case where you do have this aromaticity means enol is more stable. Okay, do we have any additional questions on this? Okay. Then what we're going to do next is this is all for the lecture slides for today. So I am going to give you guys all a chance to grab worksheets. And the problem, the synthesis problem that we're going to go over is one of the problems on the mock exam, which I will pull up on the board. And I'll give you guys a couple of minutes to work through that problem and to think about it before we start talking about it. But with that being said, if you feel confident about synthesis, if you look at the problem and you're like, nah, I don't need to listen to this, feel free to work on other problems on the worksheet or other review materials. Does this sound good to everybody? Does anybody have any questions? All right, beautiful. Yeah, of course.
For exam 4 material. So I'm like really struggling with synthesis, which I'm really glad we're going over a problem for that. But do you suggest, like, I know we have to know everything from the last exam, but like I'm like focusing heavily on like alkenes and alkyne reactions. Do you think that's a good thing to do, or should I like also like focus just as much on the exam 3 reactions?
Yeah, so that's a good question. And it is 100% up to how you feel, because on the plus side, you do have like some memory of the exam 3 reactions because
Right.
you did study for that exam. So I would probably recommend that you spend more of a focus on the exam 4 reactions, but then if you're able to just go through and review exam 3 reactions, I think that would be beneficial. She could ask about any of the exam 3 reactions, but some of the ones that are more common are like the redox reactions, so your reduction ones and your oxidation ones,
Okay.
as well as epoxide opening. So I would definitely review those and all of them if you are able to. But exam 4 is new material. There's a lot of reactions, so I would spend time focusing on that.
Yeah, like I mean, obviously, I want to study everything, but like today and tomorrow to study for.
Yeah,
I'm just trying to, like,
understandable.
hone in.
Understandable.
Thank you so much.
Yeah, of course. All right, so the problem on the board is the synthesis problem that we're going to go over, but once again, I will give you a couple of minutes before we get started on it. All right, let's go ahead and talk over this problem. The unfortunate thing about synthesis problems is that there's no one way to solve all of them. So I will try and give you the best framework when it comes to approaching these problems as a whole, but there is a lot of variability. I personally really love synthesis problems. This is my favorite part of Orgo, and I know that I am definitely in the minority there. But I think that the best way to approach these problems is to view every single reaction that you have learned this semester as a puzzle piece or as a tool in a toolbox. And what happens is you'll have to piece together those reactions in such a way where you're able to go from the starting material to the product. So you want to think about your individual reactions. You want to be able to think about the starting material, the product, and the reagents for each of these reactions to see how they can flow together in one continuous network. Now, I think the best place to start is to find where your starting materials is in your product. Because the thing is mass is always conserved. So it has to come from somewhere. So if you're adding in carbons, if you're adding in atoms in the product, you have to add them in over the course of the reaction. So it would probably be easiest to start out with this benzene ring. And we see that our benzene ring is definitely going to trace to this location. So we know our benzene ring is conserved. Nothing happens to the ring over the course of the reaction. And then we see that we have two carbons coming off of our benzene ring. Now, if we look at the places for these two carbons to be, it would be most likely that those two carbons are going to trace onto this position right here. Now, this may not necessarily be true. This is just my initial guess. When I'm looking at this problem, this is my guess. This is where I'm going to start. This is what I want to work with. So this is what we have so far. So I see that I'm adding on two functional groups over the course of the reaction. So I have two new functional groups. What are my two new functional groups that I'm adding on? I'm adding on an alcohol. What else am I adding on? An isopropyl, yes, or an alkane, if you don't want to be that, isopropyl, if you don't want to be that specific. So at this point, now I'm going to start thinking about reactions. So I know that I have an alkene, and do I know how to convert from an alkene to an alcohol? Yeah, there's a lot of reactions that allow me to convert from an alkene to an alcohol. Do I know how to convert from an alkene to an isopropyl? No, not really. So overall, it would probably be easiest to start with my starting material and to go from that alkene to an alcohol. Because that's the thing with synthesis problems. You just got to try something. You got to take a guess. You might make a mistake. You might be wrong. But overall, it's worth a shot. Now, I do want to note that sometimes it is easier to start out with the products and work backwards. So like number 7, I think. Yeah, number 7 on the mock exam, that one is one of the problems where it's easier to start off with the products and then work backwards. This one, I think it's easier to start out with the reactants and work forwards. Now, when we think about our reactions that convert an alkene to an alcohol, we can kind of group them into two different categories based on their regiospecificity. So if we look at this starting material and this product, what regiospecificity do we want here? Yeah, we're going to want Markovnikov, because we see that our alcohol is added to the more substituted position, and our hydrogen is added to the less substituted position. So yes, so we want Markovnikov addition. Now, what reagents should we use here? What reagents can we use to get Markovnikov addition on an alkene? So catalytic H2SO4 and water, that is the hydration with acidic water, right? So let me double check before I start talking. Yeah, so with that one, you are 100% right that we could get Markovnikov addition. But the downside of that reaction is, first of all, that is a very slow reaction. And second of all, it involves a carbocation intermediate. So this adds a kind of another layer to synthesis, where if you can use a reaction that does not involve carbocations, or that is an overall faster reaction, it is a better reaction to use for synthesis, which I know is a little bit unfortunate, but we're really thinking like chemists here. So does that explanation make sense with why hydration with acidic water might not be the best here? Say that one more time, I'm sorry. Yeah, so that would not be the best reaction here, because it's very slow. So it's not very convenient to perform in a lab. And also it involves the formation of a carbocation. So whenever you have a carbocation intermediate, it's also going to be slow. And you can potentially worry about rearrangements and things like that. So it's always better to use a reaction that can avoid that if possible, unless you want a carbocation rearrangement, which in this case we do not.
So could you do oxymercuration reduction?
Yes. So oxymercuration reduction would be a great choice for this particular question. Did you have another question?
Yeah, so I also thought it was nitration, and I got confused because in the starting materials in the product, it looks like where the carbons are changes, but I also wasn't.
Yeah, so let's talk a little bit more about that. Where does it look like to you the carbons are changing?
Just like we go through the positive side. I don't know if the molecules just have it right side.
Yeah, definitely. So that brings up another good point, is you can always rotate a molecule. You can spin it around in circles, and it will not change anything about the molecule, but it could be beneficial to help you better trace the reactants to the starting material. So if you wanted to rotate this guy right here, 90 degrees, you definitely could. And these are going to be the same molecule. So if that helps you better align the starting material to the products in your head, you definitely, that's totally okay. Feel free to draw all over the place. So we want to do oxymercuration reduction here. So that means that in step one, what do we use in step one? Yep. And water, and then what do we use in the second one? Yeah, sodium borohydrate, excuse me. And then also sodium hydroxide. Here, let me just erase that because I mushed it too much, and that's not easy to read. Beautiful. So then we can go ahead and look at our product from this first step, where we're going to get something like this. Okay. Now this is not ideal. We have our alcohol now, but we still don't have our isopropyl. So now we have to get thinking. We want to form a new carbon-carbon bond. If we look at our products, we see we have this carbon-carbon bond right here that does not exist in the reactants. So now let's think, what reactions allow us to form a new carbon-carbon bond? We can do carbonyl reduction. What else can we do? Epoxide opening. What else? There's one more. It's irrelevant to this example, but it's still good to think about. Yeah, so aldol condensation, as well as aldol addition, will also allow us to form a carbon-carbon bond. Now, for this particular example, I already spoiled. I already said aldol condensation will not be good. And that's just because what is the product produced by the aldol reaction? What functional group is it? An enone. What is an enone? Yeah, you got your carbonyl. Ooh, I got the highlighter turned on. You got your carbonyl, and then an alkene. This is an enone. We don't have any enones going on here, so we can rule that out. Now this is the tricky part, is how do we choose between an epoxide and a carbonyl? Yes, so we want to look at the carbons, where that new carbon-carbon bond is formed. And I can explain that a little bit. I think that it would be beneficial for those of you who don't understand this yet. So if we think about an epoxide versus a carbonyl, and we're trying to figure out which one to use for synthetic purposes, we know that with an epoxide, we'll have some sort of a nucleophile come in and attack, and we'll get a product like this. Whereas with a carbonyl, our nucleophile will come in and attack, and we'll get something like this produced. So the key is determining the relative placement of that oxygen of the alcohol in the new carbon-carbon bond. So we see that when we are working with a carbonyl, the new carbon-carbon bond is bound to that same exact carbon as the oxygen. Whereas with an epoxide, the new bond is bound to the carbon adjacent to that other carbon. Does that make any sense? I feel like I just said a bunch of random words. I'm getting very, very little confidence back. Yes. Yeah. Yeah, that's absolutely perfect. So again, just to reiterate what Ope said, she said that with a carbonyl, the new carbon-carbon bond is going to be attached to that same carbon as the oxygen, whereas with an epoxide, the new carbon-carbon bond is going to be attached to the carbon that is adjacent to the carbon that is bound to an oxygen. Does this logic make sense? Yes, okay, good. We're getting nods now. This is good. Okay, so in this particular case, are we working with a carbonyl or an epoxide? Beautiful. Okay, so then what are we going to want to do? We know we have to eventually get a carbonyl. So we can go ahead and draw a retrosynthetic step over here. We know that we're going to first of all have a protonation step. So we know that we're going to have these two steps. Does that make sense? Do we understand where those two came from? Yes. Okay. So that's the thing about synthesis problems, is that you can go back and forth and work in whatever order suits your thought process. Which means that we're only missing one step here. We're missing this step right here. Now, what reagents could we potentially use for that functional group transformation? Yeah, so CrO3, you said HCl and pyridine. So what reaction is that? Is that the only thing you could use here? Yeah, you can also use Jones. What are the reagents for Jones? Beautiful. And that is it. That is your entire synthetic route. Also, as a note, is instead of using a Grignard here, you could also use an organolithium if you wanted to. And that would be written out as So how do we feel about this problem? Does anybody else have any follow-up questions on it? Yeah. So if this was a synthesis problem on an exam, first of all, you wouldn't you could potentially be asked about a single reaction, but there's like multiple different reactions happening here. So I just want to clarify that. But oxymercuration reduction would be the best choice for that first step. It is preferred that you use this reaction as opposed to the one with acidic water that we talked about earlier. I asked Axelson about it, and she said that she would prefer that you don't use dehydration with acidic water. But she didn't say how many points she would take off, if any. So worst comes to worst, if you're on the exam and you totally forget everything in all of existence except for hydration with acidic water, then put it and you will probably get partial points.
I thought you just I didn't know you could do multiple reactions. I thought you just asked for the reaction.
Yeah, so that's a good question. So with synthesis problems will almost always be more than one step. Okay, do we have any other questions on this? Yes.
So you mentioned earlier that we don't want to use hydration for the carbocation.
Mm-hmm.
So in what situations will we know for sure to use hydration? You got it?
So are you saying when, when do we want a carbocation rearrangement to take place?
Yeah, basically.
Yeah. So give me a second to think of an example. So we could just have like a relatively simple example where we have like, that's primary. Something like this, where in this case, this would be an SN2 reaction with hydroxide. Or no, we would want to do water. Do, 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 do.
I was thinking more like in the case of like alkenes.
Yeah, but like it would stem from this idea is what I'm saying. So like you could add on another step where let's say we have we'll want to add on more functional groups if this is SN1. So this is secondary, so it would rearrange the tertiary. So then let's say we have another step where we have this and then we form like an alkene right here or something like that. Actually, it would be easier to do this problem if the alkene was right here. So like if you had a synthesis problem where you could start with this right here and have that as your product. But I don't know, we don't really talk about carbocation rearrangements a lot with alkene reactions in terms of synthesis problems. So I don't want to say that it won't happen on the exam, but I think it's less likely. I think that where you should be interested in or really looking out for carbocation rearrangements is with SN1 and E1. But at that same time, anytime you have a change to the carbon scaffold or a change to where your functional groups are attached, it would be it's indicative of a carbocation rearrangement. So like right here, our bromine is attached here, but our new functional group is attached at the carbon over.
So how is that like what I feel like what I'm asking is like, because you know like right there you did SN1. We didn't start with an alkene. And so what I'm saying is like, you know how with hydration we start with an alkene and we end up with an alcohol, but and the same thing is for oxygen, that one. In what situation would you use hydration over oxymercuration?
Yeah, and that's exactly what I was saying, is I think that it's less likely for you to get an example like that just because we don't often see carbocation rearrangements with alkene reactions. Does anybody else have any questions? Okay, hopefully all of my rambling was beneficial for you all. Let me go ahead and stop sharing.